Hey y'all, welcome back. On tonight's homework, we're going to do a little review from the first 2 days of this unit. So we'll be finding the area in between curves and also find some volumes after a region is revolved around an axis. But we'll also look at finding the volumes of objects where the base of the object is known, and so is the shape of a cross section, or at least we know the area of the cross section. And that's what we worked on today. So number one says let R be the region enclosed by the graphs of g of x, which is negative 2 plus 3 cosine pi over 2x, and h of x, which is 6 minus 2 times x minus 1 squared, and the y-axis and the vertical line x equals 2 as shown in the figure below. Now before we start finding areas and volumes and all that, one thing to note here is that we really want to be able to tell which function is which. And there's two ways that you could go about doing that. One is just to identify what type of function each one of these is, and that can kind of give it away. Sometimes that's not good enough, and we have to do a little more digging. But like on this one, g is a cosine function, and h is some kind of quadratic function, right? So cosine functions, the graphs look something like this. Quadratic functions are either like that or like this, but they're parabolic in nature. If I look at the two options here, really I see one that looks like it's going to be part of like a wave. The other one looks like it's going to be part of a parabola. So that can kind of give it away that way. But if you're not 100% sure about what the graphs actually look like, you can also just substitute in a number for x and evaluate the function you're checking to see which one it would be. So like if I check x equals 0, for instance, on the g of x and substitute this 0 into x, cosine of 0 is 1, 1 times 3 is 3, 3 minus 2 is 1, so there should be a coordinate at 0, 1 for the cosine function. And we see that right here. So that kind of matches up with our prediction that this would be cosine. Now, for the other function, maybe you're better off picking x equals 1, just because that's going to be easier to compute mentally. 1 minus 1 is 0, 2 times 0 is 0, 6 minus 0 is 6. So we have a point at 1, 6, and we can see that point 1, 6 up here. So there's two different ways how you can try to figure out which function's which if they're not labeled. One is just familiarize yourself with the parent functions graphs and what they look like. That won't always work. If there's not enough of the graph, like if this stopped at x equals 1, for instance, I don't think it would be quite so obvious that the bottom curve was sinusoidal. You might have to, in that case, you'd have to go through and check to see which one's which. So plugging in a number is kind of my go-to option there. But yeah, so that now we know that the bottom function is going to be g of x. The top function is f of x. And the boundaries of this region are going to be 0 and 2. So the first one the first part of this asks us to find the value, the area of the region. And on the AP test that this problem came from, this was on the non-calculator portion, so that we will have to find the antiderivative by hand here. So let's set it up. The area is going to be the definite integral between 0 and 2, and 0 and 2, those are the boundaries of the interval. And then we're going to do top minus bottom here. So we're going to have f of x minus g of x dx. So that is how we're going to calculate the area of R, but we are going to have to go a little bit further and actually find the antiderivatives of this difference and substitute in 2 and 0 and simplify as much as I think would be reasonable. So yeah, let's go ahead and integrate this. Actually, before I integrate, I'm going to rewrite this instead of f and g, since we're going to have to do this by hand. I'm going to write this as, oh wait, it's not f and g. What am I doing? It's g and h. There's no f here. My mistake. That's h of x. Read that way too fast. Okay, so h of x is 6 minus 2 times x minus 1 squared. And then g of x is negative 2 plus 3 cosine of pi over 2x. So we're going to have to throw in a dx after all that. And I think I'm going to simplify this a little bit so I can try to, minimize the amount of u substitutions and all that sort of thing. We do have some like terms that we can combine. So first thing I'm going to do here is to square out the x minus 1. So I've got 6 minus 2x. Oh, wait, let's not distribute that 2 quite yet. 2 times x squared minus 2x plus 1. A lot of parentheses here to be careful with. Minus, let's see, so we've got plus 2 and then minus 3 cosine of pi over 2x. Now I can combine like terms, and I don't think I'm going to distribute this negative 2 as a separate step. We'll just kind of implicitly do this as we start combining like terms. So we've got the integral from 0 to 2. Let's see here. Probably should have given you a little bit more room to work this out. So we've got 6. Well, let's start with the x squared term. So we've got negative 2x squared. And then negative 2 times negative 2x is going to be positive 4x. And now let's pull our constants together. Negative 2 times 1 is negative 2. Negative 2 plus 6 is 4. And we have this extra plus 2 is going to be 6. And so I think that takes care of everything except for the minus 3 cosine of pi over 2x. So yeah, now we got to integrate all this. We got to find the antiderivatives of each term here. So, what am I going to do? I don't really have a whole lot of room. Let's just move all this stuff maybe up here. Can I make this smaller? Oh gosh, I don't really know how I'm going to do this. No. All right. Well, I think I'm going to have to just move this up. I don't really like how that's going to look, but that'll just have to do here. Let me put this 0 up here so you can see that a little easier. Okay. So yeah, let's start getting the antiderivative set up. So we'll just do one term at a time. We're going to have negative 2/3 x cubed plus 4 divided by 2 is 2, x squared plus is 6x. And we're going to have a minus 3 times something. We are going to have to do a little u substitution on this. So I'll let u be pi over 2x. du would be pi over 2 dx. Now what I have is a 3 dx, or really a negative 3 dx, that instead of a pi over 2. So I'm going to divide both sides by pi over 2. Multiply both sides by 2 over pi would be the same thing. And then multiply both sides by negative 3. Negative 3 times 2 is going to be negative 6. So I can replace the negative 3 dx with a negative 6 over pi du. All right, and I'm going to do the little antiderivative again out to the side here, just to save a little bit of space. So yeah, I've got the integral of cosine of u, right, because u is pi over 2x, and then times negative 6 over pi du. Now the integral of cosine u, the antiderivative anyway, is going to be sine u. So I've got negative 6 over pi times sine u. Well, of course, we'd have a plus c here, but when we evaluate that definite integral, the c's are all going to cancel out anyway. So we're not just going to worry about that. So negative 6 over pi sine of u, where u is pi over 2.
I'm actually going to erase this minus 3. I'll write this as minus 6 over pi sine of u, which is pi over 2x. And we're going to evaluate that from 0 to 2. Okay. Now, I'm not actually going to use a calculator here, so I'm just going to plug in the number and then be done after that step. Okay, so let's go here. Negative 2/3 times 2 cubed plus 2 times 2 squared plus 6 times 2 minus 6 over pi times sine of, well, pi over 2 times 2 would just be sine of pi. So that's what I get when I substitute in 2. And if I substitute in 0, I'm going to get 0 plus 0 plus 0. Sine of 0 is also 0, so it's just going to be like minus 0. You don't really need to write that. But yeah, actually, can we take that a little bit further? It looks a little ugly there. I'm just going to leave it as is. Now, if you are looking to just check to see if your answer is the same as my answer, if it doesn't look exactly the same, you can throw that in the calculator to check, and I'll just let you, I did that out to the side here. And so this is approximately 14.667. So if your expression looks different and you can't tell whether or not you got it right, just go ahead and type it in the calculator. If you get 14.667, then your answer is just as good as mine. But you don't necessarily need to do that. You can leave it the way it is. Doing 6 divided by pi is going to cause you problems no matter what. Okay, part B says region R is the base of a solid. For the solid, so it's the same region, but it's the base of a solid. For the solid at each x, the cross-section perpendicular to the x-axis has an area given by the a of x function. Find the volume of the solid. So this is a non-calculator problem as well. Let's go ahead and zoom out just a bit. So yeah, we've got this, and then we've got, we don't know what the shape of the cross-section is. It doesn't actually tell us, but they do give us the formula for that area. So the volume is going to equal the integral from 0 to 2 of a of x, which is 1 over x plus 3 dx. And so this is something we definitely can handle. We're going to have to do a u substitution here because this would be the same thing as saying the integral from 0 to 2 of x plus 3 to the negative 1 dx. So hopefully you can see why we would need to do that u substitution. So out to the side, I'm going to do a little scratch work here. If you use x plus 3, then du would be dx. We have a perfect match here. So the integral of u to the negative 1 du is the natural log of the absolute value of u. So yeah, so this is going to equal the natural log of the absolute value of x plus 3 from 0 to 2. So this is going to equal the natural log of, let's see, 2 plus 3 is 5. Absolute value 5 is just 5. Minus the natural log of 0 plus 3 is 3. The absolute value of 3 is also 3. So we have natural log of 5 minus the natural log of 3. That's a good answer as far as I'm concerned, but on the if it's a multiple choice question, they might use the logarithm property that says when you subtract two logarithms with the same base, you can combine those logarithms with division. So this would be equal to log of a over b. So just a little note on log properties there. You might see this written as the natural log of 5/3. So either answer is fine on a free response, but if it's multiple choice, it's most likely going to be simplified with those logarithms combined. Okay, part C says write, but do not evaluate an integral expression that gives the volume of a solid generated when r is rotated about the horizontal line y equals 6. So y equals 6 is going to be actually at the tip top of this diagram here. We checked earlier at x equals 1, this function equals 6, so we know that that's probably going to be the maximum there. It certainly looks like it. So we're going to revolve this around that axis. That means oh, how did my h get up there? Let's move that back. That means that my h function, which is this function, is closer to the axis of revolution than the g function. So when this gets revolved around, okay, we're going to have a little hole like this, but I guess the point I'm trying to make is that the smaller radius of, the radius of the little hole is going to be in terms of h, whereas the radius of kind of the bigger one here, this is a super rough sketch here, is going to be in terms of g. I'm actually going to erase that because it's kind of hard to see. Kind of make sense of what we're doing. So anyway, yeah, it's going to be revolved around. Zoom out a little bit so we can actually see what's happening here. So that means our small radius from here to here is going to be 6 minus h, and then the big radius from the axis of revolution to the g function is going to be 6 minus g. So we're going to have the integral from 0 to 2 of pi r squared minus pi r squared. So first I'll just write that out. Pi times big R squared minus pi times little r squared. Now, I don't like the fact that I'm using capital R in two different cases here. So I'm actually just going to erase that and just plug in what R is. I'm just going to know that that's going to be the big radius. And the small radius goes in the next one. We don't actually have to solve this one, so we're not going to use the calculator or anything. We're just going to plug in, or we're just going to come up with the expression. So the small radius, like I said, is going to be this distance right here. So that'd be 6 minus h. Or I'm sorry, 6 minus, hang on, yeah, 6 minus h. Oh, I'm sorry, h is actually the small one. So it should be 6 minus g. Something just didn't sound right there. Squared minus pi times the big radius squared, which is, the small radius squared, 6 minus h. Yeah, and that's it. We don't actually have to go any further than that. That's going to be our answer. You might see, if this were a multiple choice question, that pi gets factored out as a GCF. And so you might see the answer written like this as well. So just be ready for that. Both of those are okay. All right, D is where we're going to start using the calculator. So I'll be bouncing back and forth between this and Desmos. But it says that the region region R is the base of a solid. For the solid, the cross sections perpendicular to the x-axis are squares. So on here, let me erase this now since we're not doing a revolution anymore. Don't need that line anymore. This is still h of x. So cross section, let's say from here to here, is going to go into the page, and this is going to be like a square. Each cross section is going to be its own square. Obviously, they're going to be different sizes because the distance between h and g is going to be different for any given x value. So we have the integral from 0 to 2 of our area function. Now, since it's a square, the area is the same, or sorry, all the side lengths of that square are the same, and they're all going to be equal to this length between h and g, okay, which is h minus g, and that's going to be h minus g for any x. So we've got h minus g, h of x minus g of x. Let me just make sure that h was on top there. Yep. Times itself, so squared, dx. And so this is what we're going to type into Desmos. Let me head on over to Desmos. Okay, we've got Desmos up here.
First, let's type in what h of x is. And let's scroll down so I get actually the function there. It's going to be 6 minus 2 times x minus 1 squared. And g of x is negative 2 plus 3 cosine of pi over 2x. Okay, we're really just interested in this region in here. So maybe, what we should do is, so we can just see it a little better, is put a little domain restriction in here to go between 0 and 2. You don't have to do this, but I think it'll help you to see the region a little bit better. And we could do it on both of them. Oh, didn't mean to delete that. There we go. And then maybe we also throw in an x equals 2 for good measure. Can we restrict that? Can we restrict the y values? I don't know if we can. You know what? I'm just going to delete that. We're not going to need that. So basically, we're looking for the area that's bounded by this x equals 2 as well. Okay, so now we got both those in. We can go ahead and type in the integral we're interested in, which is the integral from 0 to 2 h of x minus g of x dx. And I get, squared. Don't want to forget the squared there. And so I get 117.266. So yeah, it's about 117.266. All right, part E says the region R is the base of a solid. For this solid, the cross sections perpendicular to the x-axis are semicircles. Okay, so if the area of a semicircle, that's going to be half pi r squared. Find the volume of the solid. So since they're semicircles, right, like I said, the area of this is going to be half of the area of a circle, half pi r squared. So we're going to integrate from 0 to 2 on that half pi r squared, but the radius is going to be, if I scroll up here, the semicircle is going to be something like this, right, going into the page. And the radius here is half of the distance between h and g. So it's going to be half pi times the radius, which is half of the difference between h and g. So h minus g over 2 squared. And then don't forget that dx. Let's go ahead and type that in and see what we get here. So we got the integral from 0 to 2, half times pi times the radius, which was h minus g over 2 squared dx, and I get 46.050. All right. Okay, now that wraps up problem number 1. I don't know how much time it's been so far, but yeah, that took a while. Okay, number 2. If k is greater than 1, then the area under the curve from 0 to k is what? Okay, so k is positive and bigger than 1. We've got this curve with the area between that curve and the x-axis. So we're going to integrate from 0 to k the function kx squared dx. Now k is a constant here, so treat it like any other constant. You could factor it out. But so the antiderivative of k times x squared would be k over 3 x cubed. And we're going to go from 0 to k. So from here, we're going to plug in k, and we're going to plug in 0. And as you can see, like if we plug in 0, x 0 cubed is just 0, so that that term is just going to be 0. But if I plug in k, I'm going to get k over 3 times k cubed
So k times k cubed is k to the fourth. So I get k to the fourth divided by 3, which is the same thing as 1/3 k to the fourth. So my answer is A. Don't really need a calculator for that one. Number 3 says a solid has a base in the xy plane bounded by the x-axis, the line x equals 5, and the function y equals natural log of x. Each cross-section perpendicular to the x-axis is a square. So we're just going to square the side length, which is going to be the distance between y equals natural log of x and the x-axis. So this is going to be like your top. Here's your bottom. Okay, y equals natural log of x, by the way, looks something like this. Okay, we're bounded by the x-axis, this function, and x equals 5. Okay, so one thing we will have to do is figure out where this point of intersection is. I'll just call that A for now, and then when I pull up Desmos, we'll figure out exactly what it is. Now, each cross-section is going to be a square, where the side length is natural log of x. Okay, and the square kind of goes into it like here. You guys know I'm not very good at drawing these by now, hopefully, so I'm just gonna erase that because I think that kind of makes it look a little more confusing. Okay, so we've got the integral from A to 5 of natural log x squared dx. So yeah, I guess let's go ahead and pull up Desmos. We don't need any of these functions anymore, so I'm just going to delete all of them. We have the natural log of x as one of our functions. That's really what we're interested in there. And we're interested in the x-axis. Now, we don't actually have to type in the x-axis, y equals 0. It'll pop up with that x-intercept anyway. So it's at 1, 0. So a is just 1. So since it's not really a decimal, we don't really get a whole lot out of calling it a. I'm just going to call it 1. Okay, so we got that. That's 1. So yeah, we're going from 1 to 5, and so we just need to type that in. Yeah, we're going to take the integral from 1 to 5 of natural log of x squared dx. If you feel uncomfortable about the lack of parentheses here, you're welcome to throw that in there, but as you can see, it doesn't change your answer. We get 4.857. Okay, so our answer is B. Okay, number 4, we've got a solid has its base in the xy plane, bounded by the x-axis, the y-axis, and the function y equals 3 minus x to the fifth. If cross-sections taken perpendicular to the x-axis are semicircles, whose diameters are in the xy plane, what is the volume of the solid? So as we said before, the area of a semicircle is half pi r squared, where the radius is going to be half the distance between the two functions. So the functions here are 3 minus x to the fifth, but we also have at the x-axis, so like 0. Okay. Now let's take a look and see what that graph looks like, because I think it'd be helpful to know if that graph is above or below the x-axis. So if I do 3 minus x to the fifth, oops. Oh gosh. There we go. And we're going in between well, I guess we're going in between 0 and 1.2. And on that interval, that whole thing's above the x-axis. So I think I might just do a little sketch here so we can kind of see it a little bit easier. We're going, basically, we've got a region that looks like this, where this was at, let me hover over there again, 1.245. And each cross-section is a semicircle, so each cross-section is going to have, this is the diameter, okay, with a little semicircle coming either in or out of the page, doesn't matter, but it's going in that third dimension. And the radius from the center to the edge is going to be half of the distance between 0 and 3 minus x to the fifth. Right, in other words, like this radius is 1/2 of 3 minus x to the 5th. All right, from here to here. Okay, so let's set this up. We've got the integral from 0 to 1.245. We got a bunch of cross sections we need to add up. They're all going to be in the form 1/2 pi r squared, where the radius is 1/2 of 3 minus x to the 5th. And this is going to be what we type into Desmos. So let's go ahead and type that in, the integral from 0 to 1.25 or 45 of 1/2 times pi times 3 minus x to the 5th all over 2 squared dx. We get 3.335. We can see that our answer is A. All right, looks like we just have one last problem with a couple different parts to it. It says let R be the region bounded by the graphs of y equals sine of pi x and y equals x cubed minus 4x. This one might not be quite as obvious, but we do see the sinusoidal behavior happening here. That can happen on a cubic. Like you can have a cubic that does this. So I think it might be worth like just making sure that we're getting the right one. Now, one point that I think is kind of obvious here, that on this top function, we've got a point at 1, 0. So if I plug in 1 to either one of these, whichever one comes out to be 0, that means that this top function is that one. So like if I plug in 1 into sine of pi times 1, sine of pi is 0. So we have a point at 1, 0 on that one. And for the other one, just to make sure, if I plug in 1 into both x's here, I get 1 minus 4, which is -3. So I've got to point out 1, -3, which would be like down here, right? So that means that that top function is, let me erase all this just to save a little bit of room. It means our top function for sure is sine of pi x, and our bottom function is x cubed minus 4x. First, we want to find the area of R. So that's the easy part, right? Is to find the integral from 0 to 2 of the top minus the bottom. So we have sine of pi x minus, why did I throw in that extra parentheses there? We don't need that. So sine of pi x minus, and make sure you put this in carefully. This is where like calling one f and one g can come in helpful, because if you forget to put this extra set of parentheses here, you're going to get it wrong. But I've already made it this far, might as well just finish it off. Yeah, just make sure you put that second function in parentheses, especially if it's a sum or a difference. So yeah, let's go ahead and type this in. We've got the integral from 0 to 2 of sine of pi x minus x cubed minus 4x, all that dx. Wow, we get exactly 4. I guess, I'm looking back at this, and we actually could have probably done this without a calculator. Both of those expressions are integrable as far as our skills are concerned. We'd need to do a u substitution on this one, but this one wouldn't be that bad. We really probably could have done this one by hand. Yeah, especially, what kind of gives it away is the fact that our answer is just 4 here. But that's okay. Yeah, so there you go. Kind of wish we did that by hand now, but let's just move on. I feel like we've done enough of those. Part B says the horizontal line y equals -2. So let's go ahead and sketch that on there just so we can see right here. Splits the region into 2 parts. Write, but do not evaluate an integral expression for the area of the part of R that is below the horizontal line. So basically we're looking for the area here. Okay, so it's basically just like a new area problem, just like part A, but our top function is y equals -2. The only trick here is, and again, we probably could solve it. Well, could we solve this without a calculator? It'd be kind of annoying to solve that cubic, wouldn't it? Let's find those 2 points of intersection.
So yeah, we can delete all this. We don't need any of this anymore. We want to figure out where is x cubed minus 4x, where is that intersecting with y equals -2? Let me zoom in here a little bit. So you can see that one of these is at 0.539, and the other one, scroll over here, is at 1.675. Okay, so what we want here is the integral using those two boundaries, 0.539 and 1.675. Let me just double check that's a 5. Can't even read my own handwriting there. Yep. Of the top function minus the bottom function. So we'll have from -2 minus x cubed minus 4x, and all that needs to have a dx on it. It says we do not have to evaluate, do not evaluate, so we are just going to leave that as our answer. Letter C, the region R is the base of a solid. For each solid, the cross-section perpendicular to the x-axis is a square. So the side length of each square is going to be the top function minus the bottom function. That's going to be sine of pi x minus x cubed minus 4x, with that x cubed minus 4x being in parentheses. So let's set this up. We're still going to go back to going between 0 and 2 here. So the area of each shape is a square, and so we have to do base times height, or just base times base. That base is this distance right here. In other words, it's the difference between sine of pi x and x cubed minus 4x. So that's going to be the side length, and since we're multiplying the side length by itself, we're going to square it, and then multiply by the thickness of each cross section, which is dx. So time to go back to the calculator. And I've got the integral from 0 to 2, sine pi x minus x cubed minus 4x. That whole thing squared, and then dx. And so I get 9.978. as the volume. All right, I think we got one more here. One last problem here. It says the region R models the surface of a small pond at all points in R at a distance x from the y-axis. The depth of the water is given by h of x equals 3 minus x. So like in part C, we had a square, right? And each side length was that difference, that, f minus g, sine of pi x minus x cubed minus 4x, right? That was both this side length and this side length. But here, the base is still going to be that same sine of pi x minus x cubed minus 4x, or like f minus g. But then the height, or the depth of it, is going to be 3 minus x. So area of a rectangle is just base times height. So when we integrate, we're going to multiply those two things. So from 0 to 2, we've got sine of pi x times x cubed. No. Whoa, back up. I forgot the whole second half of that base. Minus x cubed minus 4x. So that is the length of the cross section, the distance between the two functions. So all that needs to be in parentheses, times 3 minus x dx. Okay, let's go ahead and type that in now. Going back to Desmos here. I've got like a lot of it here, so I think I'm just going to copy this. It's just that instead of multiplying that side by itself, so I don't want this to be squared, I'm going to multiply it by 3 minus x. So I get 8.369.
Okay, and that's it for tonight's homework. And that's actually it for this particular unit. I know it's a pretty short unit, but next week we will be reviewing and testing over this. So be on the lookout for the test review. In the meantime, we're also going to be doing some AP test review. So I'm going to be giving you some old reviews if I haven't already. And I'm going to want you to work those out kind of leading up to the AP test. So if you have any questions about this homework or anything else, please reach out to me. I'll be happy to go over any of these problems in more detail with you. But yeah, y'all have a great night, and I'll see you next time.